Okay, there it goes. Okay, so here's what we were talking about last time. We were talking about, well, for one thing, we were talking about vector fields and what do they look like? What are they good for? Right? And one of the things that we found that they were good for is to represent the velocity of a fluid. So if you have a fluid flow, it's a complicated physical phenomenon, and how would we represent it mathematically? And it turns out that if you think about it, a vector field is exactly what's needed to do that. Though it can be done in different ways. And we notice, though, that if you represent the velocity of the fluid with a vector field, and then if you ask the question of what is the rate that fluid is flowing through a surface, right? So it's one thing to know the velocity. That's like meters per second. But if you want to know the flow rate through a surface, that's cubic meters per second. Right? How do you account for the sort of the angle and this, that, and the other thing? And the answer was this expression called flux, written like so. Flux is the answer to that question when you have the vector field set up like that. Well, then we asked a similar question, and I did not go through the argument. I left this as an exercise for y'all, and I think this is a good exercise. If instead of velocity, if the vector field represents density times velocity, then what you compute instead of volume per unit time is mass per unit time. And I think that's kind of plausible, right? You throw in an extra factor of density, you get mass instead of volume. So just, superficially it seems kind of plausible. What's interesting, though, is that the answer is computed with this same expression. So flux in both cases. So we're going to find ourselves very often throughout the rest of this course interested in flux. And why are we interested in flux? Well, it's going to depend, sort of the context. I mean, if your vector field represents wrong color. If your vector field represents the velocity, then you're interested in flux because it tells you volume per unit time. Or if your vector field represents this instead, then it gives you mass per unit time. Either way, flux is the answer to the question. Okay. All right. Here then is an awkward reality. Sometimes we can't really talk about the velocity of the fluid at a given point. There are some weird fluids out there, right? And you'd kind of think, when you hear fluid, what you think is water, for example, right? And if water is flowing, then at a given point, the direction that the water is going is pretty well defined. You can't have, at a given point, the water flowing both that way and that way, all at the same point, right? That'd be weird. So it's just not how water works. But here's a different fluid for which that can be the case, and in fact, usually is the case. And that is, let's think about the flow of photons. Right? In case you're not aware, photons are the little tiny little particles that are what transmits light. Right? So light bulbs emit photons. Right? They're just continually emitting photons. Okay. Well, that being the case, let's think about what happens if you have a light source right there. Well, that light source is going to be emitting photons every which way. And among other things, at this point, it will be emitting, photons that are going to be going that way, of course, because the photons always go away from the light source. Sure, of course it does. But what if this is a light source also? What if you have two light bulbs? Not a weird scenario, right? Perfectly normal, perfectly common. Well, then at that same point, we would have photons going that way. And so, at this point, if I were to say, look, there's photons flowing around, photons are kind of like a fluid in the sense that it's a bunch of little particles that are all kind of moving around, like atoms in a bucket of water, right? And yet this fluid has the counterintuitive feature that at a given point, there is no single direction describing which direction the fluid is going. So how can I just say, oh yeah, the vector field, we'll just let the vector field be the velocity. Which velocity? It's awkward, right? So how do we deal with this? Well, there's a nice approach, and that is to take this formula that we have from the previous page, and here we're considering a vector field representing density times velocity. That sort of point of view on the vector field, and in that case, then flux. There's our formula for flux. Computes mass per unit time, or quantity per unit time, however you want to say it, flowing through a given piece of area, A there. And we're going to take a different point of view, though, on what this is telling us. Because previously, when we wrote down this formula, the idea was that we know the vector field representing the fluid flow, and we wanted to know how much mass per unit time is flowing through an area. And here we're going to turn it around. It's a very clever idea, but we're just going to turn it around and say, suppose empirically or whatever, suppose I can conclude how much quantity per unit time of fluid there is flowing through whichever surface I might be looking at. If I know dm dt, then can I infer what the vector field is? And the answer is yes, sure. The vector field is whatever vector field makes this work. Not exactly going to solve for it in this equation, but we can, it's different in every context, but we're going to be able to do some reasoning that will allow us to sort of reverse engineer what that vector field is based on observed dm/dt's. Okay. So I'm going to show you an example, but first a little quick disclaimer. All of the let me come back up to here. All of the fluxes that we've talked about have been through small flat surfaces, like this area A here, and it's got to be small. It's got to be flat. And I'm going to gloss over the fact that I'm going to compute similar fluxes through non-flat surfaces, but the big idea is going to be the same as for any given piece of surface, I just need to know, is the vector field cutting straight through the surface, or is it maybe kind of going off at some angle, and then I got to account for that angle, something along those lines. So I don't want to make this precise. I'm going to make what I hope will be believable arguments. But we are going to make all of this precise later on. I just kind of want to get a win under our belts here for this next idea. Okay. All right. So here is the example. Suppose I have a uniform ball of glowing gas. That's a weird thing to think about, right? But not the weirdest thing you probably ever heard of. I mean, after all, neon. Like, you've seen neon signs, right? That's a glowing gas, right? So suppose that instead of in the shape of a, Eat It Joe's, suppose it is a spherical ball of glowing neon gas. And how does the light flow around? Well, gosh, extremely complicated, because there's, for example, this little particle of neon gas, and it's sending out light every which way, right? And then there's this particle of neon gas, and it's sending out light every which way. And there's a bazillion more little particles of neon gas that are sending out photons every which way, right? So any given location we might be at, there's a bunch of different directions, you might say. So at that purple point, the green photons are going that way, and the blue photons are going this way, and the here's an orange piece of gas, and the photons are going that way, etc. Right? So complicated story. Okay. So a couple of key observations I want to make. We're going to derive the vector field representing this flow of photons. First observation I want to make is if there's a piece of neon gas over here that's outside of a surface that I'm interested in, and let's start by considering this piece of surface right there, that sphere. In terms of how much flux through that sphere, this orange light source contributes nothing. And here's why. When photons first hit the sphere, they're going, you might say, inward through the surface. But then they keep going, and then over here, they go outward through the surface. So there's just as, at any given point in time, there's just as many photons going out through the surface as there are going in through the surface. And so in the net, that's a wash. Right? Does that make sense to everybody? So if I'm interested in computing the flux through that purple surface, I can ignore all of the neon outside of the surface. Pretty neat observation. Okay. Related next observation. What about the gas on the inside there? Let's see here. I suppose I've got a little piece of neon right there. And that piece of neon gas is emitting photons. What can I say about the photons being emitted by that little piece of gas? What fraction of those photons pass through this surface? Answer, all of them. Right, so this photon going that way, well, it passed through the surface right there. And this one going that way, well, it passed through the surface right there. They got to get out, right? Photons move. Straight lines, nonstop. So they're all going to leave that little surface. Believable? Okay. All right. So the conclusion we get from this then is, if you want to know how much flow of photons per unit time are going through the surface of the sphere, well, look, it just depends on what the volume of the sphere is, because the volume of the sphere tells you how much gas is there inside of there, and the more gas, the more photons, the more flux. And the gas that's outside doesn't matter anyway. So all that matters is the volume of the gas that's on the inside. Now there are some constants such as per unit volume, how much gas is being emitted. Is this a bright neon or is this a dim neon? And stuff like that, and that's all factored into this constant K. And so we don't need to know the constant, but the point is it's proportional to the velocity. To the volume, sorry. Is everybody happy? Okay. All right. Okay, next thing I want to talk about. Let's, with that established, let's think now about a a centered sphere, such as this one. Centered sphere, centered at the origin, right? And we're going to try to think if we can understand something about the flux going through that sphere. And I am going to note first that the vector field ought to be radial. So what I mean by radial, the vector field should always point outward, away from the origin, along radial lines coming out of the origin. So radial vector field. Why should we have a radial vector field? And this is going to come out of the symmetry that we're assuming. We're assuming that we have a uniform ball, and because it's a uniform ball, short version. What else could the vector field possibly do? Right? Could the vector field possibly point that way, off the radial line? If it did, that would suggest that somehow there was more light coming from over here than there is coming from over here. Right? Everything's symmetric, and so the field line, the vector field arrow can't point in any it can't favor any direction over any other, and so it would have to be kind of outward or inward, I suppose. What do you think about that? Believable, also. Okay. And then easy observation from that is that keeping in mind that we are looking at a centered sphere, and centered spheres have radial normal vectors, right? Symmetries of the sphere. Normal vectors perpendicular to the sphere have to be radial like that. That means both F and N are radial, and that means that this dot product, F dot N, the angle in between those two vectors is 0. The cosine is therefore 1. N is a unit normal vector, and so all that's left in this dot product is the magnitude of F. Okay. All right. So that's all kind of set up groundwork, and with all that established, we're now ready to do the calculation. By the way, this is a bunch of clever observations that we're making that will result in an answer, but I think this is a healthy argument to see. So, okay, we're going to start now with our sort of definition of the vector field. We're going to define the vector field to be the thing that makes this equation work, right, as previously discussed. Normally, the vector field allows us to compute quantity per unit time. We're going to use quantity per unit time and say that the vector field is that which makes this formula still hold. So this is our starting point. We argued over here that the quantity per unit time is proportional to volume. Okay. We argued here that this dot product is the magnitude of the vector field. And it's kind of all over but the shouting at this point. So in particular, that means, let's not forget that volume is 4/3 pi r cubed. Keep in mind we're talking about this sphere here still. Volume is 4/3 pi r cubed. Area, let's not forget, is 4 pi r squared. And so our original purple equation becomes then this equation in which you can solve for the magnitude of F. It's just a little bit of quickie algebra there. You solve for the magnitude of F, and now here's what we know a tremendous amount of information about this vector field. We have a radial vector field. That means it's got to be a multiple of the X vector field. And I also know that this magnitude is this particular constant times the radial distance away from the center. And there's only one vector field that has that property, and that's this one right here. So we found the vector field. Now this is like I say, it's kind of a tricky example, but this is a useful thing. If you have a vector field like one of these weird photon vector fields, fluids flowing every which way, passing through each other and such, which thankfully water never does, air never does, right? Then an approach like this can allow you to find the appropriate vector field. What do you think? Everybody okay? Yes?
What does the X vector mean?
Yeah, so that's this vector field. It's we talked about this vector field last time. Well, we talked about the two-dimensional version of it here. So the vector field, the field vector at a location X, right? The idea is that at this location X, the field vector is it's the position vector for that location X itself. You remember we talked through what that means the vector field has to look like, and it's kind of like this. And so you see what I was claiming is that this is a sort of a starter, world's easiest example of a vector field that's radial, right? And we knew that our photon flow field had to be radial, and so it's got to be this times something, and as far as directions go, it's identical to this, and it's just a question of magnitudes. Does that make sense?
Yes.
Yeah. Cool. Yeah, good question. Okay. All right. Okay. Let's see, where are we? Yeah, there we go. Okay, so one other thing I need to tell you about vector fields representing fluid flows, and that is I want to define something called a flow line. This is a pretty natural idea. If you have a fluid flowing, for example, let's take the air in this room, right? And I'm going to speculate that, I'm standing here talking, I'm blowing air that way, but I'm kind of on this side of the room, and so I'm pushing air that way, and maybe there's a fairly slow, but non-zero, perhaps kind of like this kind of rotation of the air in this room. You know what I mean? So the air is kind of flowing around in sort of circles in the room. if that were the case, what would happen to imagine a little balloon, a little perfectly weighted balloon whose buoyancy is, total buoyancy exactly 0, so it just kind of floats. Like after a party when the helium balloons have kind of lost just enough of the helium and they just kind of float. Sort of the perfectly balanced things, right? So that balloon, if the fluid is kind of flowing around in a circle, you would expect that balloon would kind of follow such a circle. So that's called a flow line. And so as a visual example, I'll go back a few pages here to this. Here's a vector field and a flow line. If we were to imagine what would happen if we had a particle dropped right there, well, the particle would cruise around like that. It would just follow and do exactly what the fluid tells it to do. Right? So this red curve is a flow line for that vector field. Now, how would we get our hands on that? How would we compute what this curve is? In some sense, we just want to look wherever we happen to be. The vector field is indicating which way the fluid is going, and the particle should be doing exactly what the fluid is doing. And so whatever the vector field is, that should tell me what the velocity of my curve is. And that's all that we have to write down in order to define what we mean by a flow line. So the velocity of the particle is whatever the velocity of the fluid is. Wherever it is that you happen to be. Right? So if at some moment t, if you are at location x of t, whatever the velocity of the fluid is at that location x of t, that velocity is what your particle velocity, x prime, needs to be. And then don't forget, if this is a case where the vector field represents the fluid by way of its velocity, then the velocity is the same as f, and then altogether what we get is the appropriate differential equation for the flow lines. That x prime is f of position x. Now, we don't know how to solve these differential equations. Y'all haven't had, I believe, I understand, a course in differential equations yet. Probably most of you, maybe one or two of you have. So how to solve, in fact, this is called a system of differential equations because this is a vector valued, this is a parametric curve, right? So this is like x, y, and z, all as functions of t. And they are various different functions, depending on what the vector field is, of x, y, and z. So how do you solve such a differential equation? That is a topic for Math 353. But this is where the differential equation comes from. Okay, just as a quick example, and again, we don't know how to solve the differential equation, so I'm not going to show you where this came from, but this is that vector field we had a few pages back, and we can directly confirm that this is a flow line, because if you take this x, plug it in there, right? If you take the derivative of that curve, you get the same thing as if you were to evaluate the vector field at the points on that curve. And it's just algebra, a little bit of algebra. Take the derivative, right? Keep in mind this is x, this is y. Compute the vector field, find they're the same thing. Okay. Everybody on board? Alrighty. Okay. So one last little note before we go on to the next thing, and I'll remind you that I've given you a couple of different what I'll call metaphors, physical metaphors for vector fields. On the one hand, you can think of vector fields as representing forces, gravitational fields, for example. Right? We wrote down the vector field for a gravitational field of a point mass source. And electric fields. And of course there's various other kinds of forces in the world that you might represent with vector fields. So the point is, vector fields can represent forces, and that's good intuition for certain kinds of calculations that we're going to do in this course. But here's the thing, vector fields can also represent fluids, as we've been talking about for the last little while here. 25 minutes today and a little while before that. We've got two different ways of thinking about vector fields, two different physical, again, manifestations or metaphors, whatever you want to call them, for vector fields. So the problem is that it tends to be that sometimes students will decide they like one or the other of these better, and will then kind of cling to that one. I'm going to think about everything in this course with, let's say, forces. I'm going to think about everything in this course in terms of forces, and I don't like the whole fluids thing. I'm going to ignore that, right? Or vice versa. Maybe you like fluids, and the forces thing's a little bit mysterious. I want to give you all fair warning that you really do need both. There are certain things we're going to do with vector fields where you really need to be able to think of the vector field as representing forces. It's going to be necessary to understand it as forces. And there will be certain things that we're going to do with calculus of vector fields where you're going to need to be able to understand it from the point of view of fluids. So anyway, just a heads up, make sure that you're comfortable with both of these examples. All right. Okay, so the last section of chapter 3, there is something kind of weird about this section. It's arguably a little out of place. It's a little bit kind of premature. They're going to introduce some ideas here in chapter 3, in section 3.4, that we really don't have the tools yet to fully make sense out of. So the book, I believe, introduces these objects, these ideas here, way early here in chapter 3, I think to kind of plant the ideas and let them be kind of, fermenting in your minds so that when we get around to chapters 6 and 7 where they're going to be a big deal, they're going to be, they're going to come up prominently in chapters 6 and 7, that you will have already kind of gotten a little accustomed to the ideas, right? So I think that's the idea. But there's an awkwardness to it that I'm going to have to make some claims that are going to come seemingly out of nowhere with no justification, and I'm not going to prove them, and I'm not going to really do anything other than show an example that tracks with my claims, and that's all we can do here. So, apologies, that's the circumstance, and I do promise that we'll clean it up quite a bit, practically completely, maybe not quite, when we get to chapter 6 and 7. And so for the moment, just trust me. And we'll, like I say, we'll fill in the blanks later. Okay, all right. So starting off with the idea of gradient. Y'all remember the gradient. A couple ways to think about the gradient. It's an algebraic shorthand, convenient bookkeeping system, right, for understanding directional derivatives and stuff. It also has geometric interpretations, and that's nice. Various cool geometric interpretations. I want to think of this now a little bit differently. I want to think of the gradient as being sort of something being done to the function f. And just, if you look at the notation, if you're going to make a notation to represent what is this triangle and what does it do to f, you'd have to write it as a vector consisting of partial x, partial y, partial z, which, when you apply to f, give you the gradient that we know we have. Right? So this, if you kind of, in some sense, distribute the f, would give you that as it is supposed to. All right. So we're now going to talk about, can we view this thing by itself? We have not done this before, right? Previously, whenever we write this little upside down triangle, it has always been followed by a function. And that the whole thing together we refer to as the gradient. Now I'm going to talk about the upside down triangle by itself, independently. Very weird. So you know, this is called the del operator. Students mistakenly sometimes call it the gradient operator. That's not correct. The gradient is what you get when you apply the del operator in this particular way to a function. It's one of many things that you can do with the del operator. It's not the same as the del operator. So please don't call this the gradient operator. It's not what it is. We're going to do various different things with the del operator. It's all kind of what I'm going to call symbolic notational abuses, I think is a fair statement. But this is not the first time that you've seen notational abuses in this class. I'll remind you the formula that we have for the cross product. It's a kind of we write it as a determinant. Determinants are supposed to be what you do to matrices. Matrices are supposed to have elements that are numbers. That whole cross product formula thing has vectors in place where there should be numbers. And that's uncomfortable. That's weird. That's a notational abuse. Right? But it's a notational abuse. It's really convenient, and it's, I like to call it victimless crime. It's like, yeah, it's not really right, but it also always gives you right answers, and so it's very handy. So this is going to be the same kind of a thing. This kind of looks like a vector. Sort of. Right? But vectors are supposed to have elements that are numbers. D by dx, by itself, alone, not a number. Right? So let that part slide. This is another one of these kind of very convenient little crimes that's it's awfully convenient, and it's never going to lead us astray. So go ahead and let that slide. Okay. All right. So here's the first thing we're going to do with the del operator. We're going to define something called the divergence of a vector field. Notice here's our del operator. Let's see if I can be more careful with how there's our del operator. You can see it right there. There's the various partials, x, y, and z partials. And then we have this vector field here, F. You can see its components here, F1, F2, F3. And this construction that I have, which is the divergence, notice that it's a dot product. I've got it written as a dot. And we read this, by the way, literally as del dot F. Del dot F, otherwise known as divergence. And of course, the way you take a dot product is, well, it's this, right? If you were to pretend for the moment that del is a vector, right? And then do the dot, whatever that means, to this thing that we're pretending is a vector. This is what you'd get. And this is exactly the formula for divergence that is going to turn out to be a very natural, useful thing. Again, later on, chapter 7, 6, 7, around in there. Okay. All right, so this is just a definition. I remind you again, we do not have the tools to be able to really make proper sense out of this right now. We will develop those tools, and we will revisit divergence again in chapter 6 and 7, and we will make much more sense out of this than we are right now. For the moment, I'm going to do a very hand-wavy claim, supported only by a couple of examples, and that's really all we can do. So that said, apologies made. Here's what divergence represents. Divergence represents, in some sense, how much a fluid is flowing away from wherever it is that you're evaluating the divergence. The extent to which the fluid is flowing outward away from where you're evaluating it. That's what it is. Again, we do not have the tools to justify this. But let me show you an example so you see at least what I'm claiming. Here's a vector field. Familiar vector field. Nice, easy formulas for a vector field. I want to compute the divergence now of this vector field. I'm going to compute the divergence at the origin, just for convenience. There's the origin. And the way we compute the divergence, again, don't forget, we've got our del that we're dotting with the vector field, which is x, y, z, as you see right there. Right, so this is just computing del dot f, or as you might say it, the x partial of the first output, the y partial of the second output, the z partial of the third output. Happens to be really easy algebra. That divergence ends up being 3, which is clearly positive. Now let's revisit the claim here in the context of this question. The claim is that this thing we just computed should tell us how much the fluid is flowing away from the origin, which is where I'm evaluating this divergence. And notice it kind of, again, it's consistent. This doesn't prove anything, but you can imagine that this vector field is representing a fluid flowing outward away from the origin. And the divergence, being a positive number, is saying that, there is a positive extent to which the fluid is flowing outward away from the origin. Is that cool? Okay. So this is what I mean. When I say that divergence tells you how much the fluid is flowing away from the point where you're evaluating it, I mean flowing away a la this picture. Okay. And then if this divergence value were larger, then there would be longer field arrows. There'd be greater velocity or whatever it is that the vector field represents, but greater flow away from the point. If it were smaller, then it'd be shorter arrows, less flow away from the point. If it were negative, inward flow. Does that seem reasonable to y'all? So again, we'll make a lot more sense out of this later. Before we go on to the next example, I want to get my eraser to work. There we go. Talk about the physical interpretations. Right. So keep in mind this. We're interpreting this as a fluid. So given that this is representing a fluid flow, we've got this positive divergence. So there's fluid flowing away from there. What does that mean physically? So, well, here's the thing. There's two different possibilities. And this is a source of confusion. It certainly was for me when I was first learning this stuff. The fact that there are different possible physical explanations, it's easy to kind of conflate these little scenarios. But let's talk about them one at a time, and then we'll compare. Pretty easy interpretation you could take is that, maybe this is a fluid of gas or something, and if all the gas starts rushing away from the center, well, then there's going to be less gas there, right? There was a certain amount of gas, then it all left, now there's less gas, right? So that's a natural interpretation, is that the fact that there is a positive divergence is making there be less stuff as time passes. Does that seem reasonable? You could imagine that scenario, right? Here's the problem. That's not the only physical scenario. Here's a totally different scenario. Instead of this being a gas, of which there is a finite amount, and if some leaves, then there's less remaining, right? What if instead it's a totally different kind of fluid, namely photons? Maybe this is a light bulb. And if there's a light bulb right there, well, then there's going to be a flow of photons outward away from the light bulb. The amount of photons isn't decreasing, right? If you have a light bulb, like there's a light bulb there, are we losing photons? No, of course not. It's making photons. The amount of photons is constant. They're just spewing out of the light bulb. So that's the other interpretation. If so, for example, in the light bulb metaphor, this might be where fluid is being created. Not that fluid is just leaving and therefore having less of it, but it's being made there in the first place. So in the real physical world, it could be some combination of both of these. And we'll talk about some examples of that later on. But certainly, you can. I think it'd be a good goal at this point to try to get comfortable with how that picture could be interpreted in either one of these senses. Is that cool? Questions? All right. Okay. So here's another example. Vector field. Y'all can draw a picture of this vector field. Nice exercise to think that through on your own, right? You should be able to draw a comparable to this level of detail anyway, picture of this vector field. It's not a hard one. So make sure you can do that. And now let's take the divergence, and again, keep in mind, divergence means we're going to do del. Here's the del operator. And here's our vector field components, y and 0. And again, the divergence is that dot product, just computed like so, which turns out to be 0. And I think that actually is pretty consistent with what we would expect from that picture. So if this were a fluid flowing, and if I were to think about some region of space, let's say this region here, notice, kind of like how we argued before, the amount of fluid flowing in is always the same as the amount of fluid flowing out. Right? You can just follow the flow lines. There's just as much going in as there is going out. So altogether, I mean, I guess, yeah, there's kind of an outward flow, but there's also kind of an inward flow, and they kind of cancel each other. And altogether, are we accumulating fluid? No. I mean, is this a fluid source? Is this where the water is coming from? If water were flowing like this, let's just say that'd be weird, but if the water were flowing like this, is this a water source? No, not at all. So, perfectly consistent with the divergence being 0. Is everybody happy with that example? Makes sense? Yes?
What did you do with the dy over dx?
One more time, I'm sorry.
What did you do with the dy over dx?
Yeah. So what you got to keep in mind, what we're doing is we're computing divergence, and divergence is, I'm just getting my pen set up here, del, which I've got highlighted in green down here, and then dot the vector field. So here's the first coordinate of the vector field, that's y, and then here's the second coordinate of the vector field, that's 0. And so doing the dot product, the first coordinate of del is d by dx. The first coordinate of f is y. Is that cool?
Mm-hmm.
Yeah. Satisfying?
Yeah, and so it equals 0
Just because.
we solved for that, or that was...
Yeah, no, it's just the algebra. Yeah, the partial of y with respect to y is not. It's independent of x, and so we're basically taking the x partial of a constant here. So this is 0. The y partial of 0 is 0. So it just works out to 0. Anybody else? Okay. All right. Alrighty, here's the next thing we're going to define, and highly analogous in the sense that I'm going to write down a formula that is notationally sketchy, and I'm going to apologize that we don't have the tools to understand this yet. And then I'm going to make an assertion coming entirely out of nowhere with no justification as to what this actually represents, and promise that we will make sense out of it later, right? We will fill in a lot of, not quite all, but a lot of the details later on, chapters 6 and 7. So here, the thing we're defining is something called curl. The curl of a vector field. So again, it comes off of the del operator. You see the del operator right there. And del is something that you do to a vector field f, which you see right there. And notice that my formula for curl is a cross product. And don't forget that here, this is how you compute a cross product. Cross product is this weird symbolic determinant. So this is even weirder in the sense that I'm doing a symbolic determinant for the cross product involving a symbolic vector, namely the del operator. So very strange, very sort of super sloppy notation. But again, very convenient and gives you the right formula and victimless crime and all that. So it's called curl. Now, why are we interested in curl? What does this mean? What does it look like? What is it good for? Again, promise I'll fill in the blanks later. Again, the book makes this choice to do this topic way early. So what it represents, curl represents the amount and the axis around which the fluid circulates. The fluid is kind of rotating in some sense around. It's measuring a rotation of the fluid. And that rotation, if you think about it, I mean, there's different ways that fluids can rotate, right? I could have fluid rotating like a tornado is a rotation of the air fluid, right? But it's a rotation specifically, most of the time anyway, around a vertical or mostly vertical axis. But you could have air that's rotating this way, right, around a horizontal axis. Or instead of this way, maybe it could rotate this way, right, around that axis. So you can rotate fluid around any axis at all. And curl, by which direction the curl vector points, it's going to be telling you what that axis is that the fluid is rotating around. And by way of its magnitude, it's going to tell you, in some sense, is it a lot of rotation or is it perhaps a gentle, slight rotation? So let me give you an example. Again, it'll be easier to see what I'm claiming when we see it in action. Here's a vector field that's not one we've seen before exactly, but it's pretty reminiscent of something we've seen before. We've seen before the idea of f of x comma y being negative y comma x. Hope you all remember that. That's the one where the fluid kind of rotates around the origin. This is different in the sense that now this rotation, if you will, kind of around the origin is happening at all values of z. So at various different values of z, imagine this same rotation, up there and up there, etc. Okay, so this is a three-dimensional rotation, but instead of a two-dimensional fluid going around the origin, this is a three-dimensional fluid going around the z-axis. Is that cool? Everybody see what we mean? Okay. So, now let's naively, blindly compute the curl. Keep in mind curl is, wrong tool here. Okay, so del. There's del. Here's our vector field. Here's the cross product of del and f is again kind of all of that. So there's del cross f. Now I've skipped all the algebra, but if you go through and think about remember you go across the top and then this and there's a whole process for doing that cross product, and you'll find yourselves taking, the z partial of x and the x partial of 0 and the various different partials that you'll be taking as a result of that. And when you add it all up, what you'll find is that the curl is this vector 0, 0, 2, which, as promised, indicates the axis that fluid is rotating around. Is that cool? Now, again, this doesn't prove anything, right? This is just an example of what we're claiming here. That the curl tells you about the axis that the fluid's circulating around. And then there's also the matter of the magnitude. The fact that the magnitude is 2 here is some indication of how much the fluid is rotating around that axis. And I can't make this precise. Again, we just don't have the proper tools yet. And this will all get quantified and made precise when we get to chapter 6 and 7. But This being 2 indicates how much rotation there is around that axis. If this were a 17 instead of 2, this would be a much stronger rotation. There'd be longer field lines going around, much more fast rotation. If this were negative, it would be going the other way. All right. Yeah. Please.
Can we represent clockwise circulation?
Yeah. So let me comment on that. So you've noticed that I wrote over here counterclockwise. So counterclockwise, in some sense, as seen from the head of the curl arrow, and so as seen from up here, that rotation is counterclockwise. Right? So if the curl were the other way, if the curl vector were, and in fact I have an example down here, this curl vector, you see, points the other way, it points down. Now you have to ask yourself, what would it look like if I were down here, looking up, right, and if it looked counterclockwise from down here, if it looked counterclockwise from down there, then it would look clockwise from above, which is consistent with what we have here. I mean, there's kind of a sort of a clockwise, you might say, rotation there. Does that make sense?
Yeah.
Okay. Yeah. Okay. Now I am just now noticing the time, and I think I am in. Let's see, 4:20. Yeah, I'm out of time. So. Super quick, take a look at this example. I claim that you would expect there to be no rotation here. You look at this vector field, it doesn't look like it's rotating at all. Confirmed by curl. And then if you look at this vector field, even though the flow lines are all straight lines, nevertheless, if you were to imagine something kind of floating here, notice the vector field is kind of pushing on that side in that direction, and it's pushing on this side in that direction. And wouldn't you guess that this little boat, or whatever it is that I have in orange, it would be rotating, wouldn't it? So the flow lines of the fluid are straight, but there's still a circulation of the fluid because that boat would sit there and be rotating about like this. So positive. So a non-zero, therefore, amount of curl. Okay, we're out of time. Drawing the line there. Y'all have a great Monday. See you on Wednesday. Oh, and a quick update on the exam grading. The hurricane blew out power at my house for a while, and so my big plans of doing Gradescope were foiled. And so my revised plan is to be grading this week. My hope is to get it done by Wednesday. My more realistic hope is to have it done by the end of the week. So, see you later.